All right, so I'm Rangan Sukumar, and I'm a data scientist at heart that works and drives the vision inside Cray that every supercomputer that we build going forward will have analytics and AI on it. So as a data scientist, getting to know HPC best practices, 4 things that we've tried working on and we've seen some really good impacts is the following. Right? So just like you treat every HPC app, where you start with what the app looks like, then you go through the process of fine-tuning it based on identifying parts of parallelism and parts of where the I/O needs help and so forth, being able to leverage your high-performance interconnect and cleverly creating your algorithm to swap compute and I/O, and then being able to overlap that through the interconnect. So if you take those 4 best practices and apply it back to 3 popular things that every data scientist uses today, be it graph analytics, where you're trying to infer something from unstructured and structured data put together, be it unsupervised learning using matrix methods like NMF and PCA, or be it deep learning, which is all the buzzword that's going on around, we're able to see tremendous impacts. For data sets that are 1,000 times larger, we are able to see 100x speed up. I'm going to show you that in a second. On unsupervised methods that I'm talking about, for the same size cluster, you get 2 to 26x better performance over open source tools like Hadoop and Spark. And for Spark, we're the only ones that are able to run at 1,000 plus GPUs at 95% plus efficiency. Right. And so this is the first set of results that we have with the Cray graph engine. You've seen us talk about the RDF platform, and Steve Reinhardt mentioned a couple of sentences about it. So that was on the left. Now we are also able to scale some of the work that Graph 500 kind of workloads that happen. So it's one platform that's able to do both pattern search and graph theoretic mining at 100x the performance. So you're looking at a logarithmic axis over there. So 100x performance on arbitrary ad hoc search, 100 times performance on graph theoretic algorithms like PageRank, connected components between a centrality, et cetera, et cetera, et cetera. So that's graphs. And then we've got non-matrix methods, the matrix methods, non-matrix vectorization methods, PCA, and so forth. This was done at Cray, where we basically swapped the linear algebra stack that comes with Hadoop and Spark with an MPI-based layer. And you're starting to see anywhere between 2 to 25x difference there. So this is, again, finding the limits of what Spark can do at scale. Right? So we kind of tried scaling Spark above 1,522 nodes, and it just couldn't. We just ran a comparable workload just to show that we can run it a little bit bigger. And interestingly, a follow-up paper on the exact same conference from Oak Ridge showed that for the same kind of data sets, they could do 400 times better by doing the strong scaling on a more number of cores rather than 1,500. So that's 2 on metrics methods and graphs. And more recently, we've been working on deep learning, where our plugin is agnostic to both CPUs and GPUs. So both Intel and NVIDIA can if you have investments in either of them, you're able to see the differences. So this is not comparing the gRPC TensorFlow versus somebody else. So when you do a gRPC out-of-the-box TensorFlow implementation, compare it against what you already get with an MPI conversion, you get a 2x performance difference. This is trying to compare an MPI-based code that's multi-node distributed software and what we have with Cray programming environments. You're starting to see that even at 8 nodes, which is a single node level, you're starting to see 10% improvement on a single node, and all the way up to 60% on the efficiency, the scalability efficiency on CPUs. And that translates to about 3x when you think about throughput. And so when you translate that to XC on GPUs, and again, this is not a dense node cluster. This is a 1:1 CPU GPU cluster. We are seeing about anywhere between 5x to 3x to 5x again on both efficiency and throughput on different kinds of models. So I think with that, I do have a talk after lunch where I wanted to get into the details of what we learned from these kinds of activities. And of course, we got in the news for doing several of these works, running deep learning at scale. So we've got the 18,000 GPU machine that we ran on. We've got the 15 petaflop paper. And there's going to be more news coming out recently that we worked with Microsoft on scaling some of the things up. So with that, I have 1 second left. So I timed it perfectly. So.